Hello everyone, welcome back to another very interesting question. This is related to angular momentum conservation. Good question, properly within IIT JEE advanced syllabus. So let's read the question. A bead of mass m, this is a bead you have, is attached to lower end of a light inextensible thread. So this is a light inextensible thread, lower end is attached to the bead there. That passes through a small frictionless hole. So there is a frictionless hole here. The thread goes through frictionless hole in a horizontal tab, a top there. So this is a horizontal tabletop we have. This is a tabletop we have. Through that it is passing. The upper end of the thread is held by somebody motionless. The bead is pulled aside and projected horizontally so that it moves in a circular path. So it creates a conical pendulum there. Circular path of radius capital R with a speed V0 at a particular depth below the tabletop. So they had given the speed V0 and they also had given the radius of the circle capital R. V0 and capital R are given. Depth they didn't give. Depth is, let's say, h there, that we need to calculate it using geometry. Now the question is, find work done by the external agent in pulling it slowly. The holding hand has to pull it slowly upwards to reduce the depth of the circular path from h to h by 2, half the initial value. Then what is the work done by the external agent is what they are asking. So the question strategy would be, first we need to apply Newton's law, conical pendulum problem. Newton's law we will apply centripetal acceleration, vertical acceleration and so on, and get a relation between velocity, radius and height. So that's the first part. The second part is work done equal to change in kinetic energy plus change in potential energy. Work done by external agent equal to change in mechanical energy of the system. There is no other dissipative force here. So this is a basic strategy, and if the equations are not enough, you can definitely use angular momentum conservation here. Angular momentum about the axis passing through the vertical axis passing through O, center of the circle and the hole there. About that axis angular momentum will be conserved here. If you look at the forces, there is one tension which is passing through that point, so torque about that point will be 0. mg will produce torque, but that is going to be along horizontal direction. It is not along the axis of rotation there. So about that axis torque is 0. mg produces torque but not along that axis. That will be horizontal torque, you have it. So angular momentum about the axis can be conserved if required, if the equations require them. So one more important point here, slowly they are moving. When they are moving it slowly, then radial velocity and vertical velocities can be neglected. Radial velocity is 0, vertical velocity is also 0, slowly it is being pulled. That's the assumption we are taking it. Okay, now let's go into the derivation part of it. So first thing is about applying Newton's law. Simple, one particle is there, you have tension and mg. Tension is resolved into components, vertical component t cos theta, horizontal component t sin theta. The particle moves in horizontal plane, meaning it has no vertical acceleration. It will move vertically a little bit slowly, so vertical acceleration is neglected. So t cos theta should balance mg, that is vertical equilibrium. Horizontally t sin theta is the force which produces that centripetal acceleration. So t sin theta equal to m into v0 square by r, that is t sin theta. By just taking the ratio you get tan theta equal to v0 square by rg, but tan theta they didn't give, we need to eliminate it. So you look at the geometry, tan theta is nothing but opposite side by adjacent side. From there you will get a relation between r, h and v0. So you can write it as v0 equal to r root g by h, otherwise h is equal to r square g by v0 square, either way you can write it. So we got the relation using conical pendulum, simple idea. Now if I replace h with h by 2, because depth is going to be reduced to half the initial value. If you replace h equal to h by 2 and capital R equal to small r we have to find there, where the radius of the circle at that depth. If you write the same expression, this will turn to this. V is replaced by V0 is replaced by V, capital R is replaced by small r, h is replaced by h by 2. You will get the formula by using again same Newton's laws. So this is what we have. Now this small r is not known to us, and we will not be able to get it from Newton's law. Newton's law is already exhausted, we have used it. So now we go for conservation of angular momentum. The fact that about the axis there is no angular momentum changing, so you can write m into r into v perpendicular from the axis of rotation is constant. From there you will get small r equal to v0 into capital R, and that I am going to substitute in the second equation. So we get v from there, v equal to 2 power 1 by 4 times v0. right? That's a part, and then small r also you get it. When you substitute v from there, you will get a small r also. So now we have v and small r. H is also known to you. H, we have got this formula now. Everything is available. Now we can go for finding the work done by external agent, which depends on change in kinetic energy and also change in potential energy. Change in potential energy is mg h by 2. H by 2 is the height raised, and h we have already got it. We will substitute there. Change in kinetic energy meaning half m into v final square minus v initial square. V we just got it. Substitute there. Add them, you will get the total work done by external agent there. That's the answer there. So with that, the solution is completed. I hope you understood. If you have any doubt, please put a comment down there, and thank you very much for your time. Until next time, goodbye.